Welcome back to the channel. So right away, let's talk about last week's video. Well, if you didn't get the memo, the bottom line is I screwed up and I did my calculations wrong. So on our epic road trip to nowhere, we actually got 40 miles to the US gallon in this contraption and not 19.6 miles to the gallon. That's not too shabby considering the petroleum battery is not an efficient way to generate electricity. Keep in mind, this is not a fuel economy project. You see, the goal of this project is to get an electric golf cart back on the road without using expensive and heavy batteries. So yeah, we drove an electric golf cart 10 miles at an average speed of close to 20 miles an hour, and we didn't have batteries. So I would say that's a success. And getting an electric golf cart back on the road without using batteries is possible. Actually, let's not forget our secondary goal, and that's to do this as simple as possible. And what that means is we aren't adding any bells or whistles to the basic system. However, in version 2, we will have a bunch more features. But right now, I'm focused on making this as simple as possible and using as many off-the-shelf components with little or no modifications. So if you're new to this channel and to this project, the good news is we've already done most of the development and basic testing, and the system works fantastic. The heart of this system is a 212cc Predator engine from Harbor Freight that's coupled to a Jeep Liberty 140 amp alternator. The alternator is obviously generating the electricity that we need, but keep in mind we're also dual purposing the alternator and we're also using it as a DC motor controller. The fact that we're dual purposing the alternator makes this project extremely simple because we don't have or need any extra electrical parts in the system. The way we're using the alternator as both a power source and a DC motor controller is unique, and it's important to understand this is not a conventional way to use an alternator. Once you wrap your head around the fact that we're using the alternator as a DC motor controller, it becomes clear why we don't need any extra stuff like batteries or supercapacitors in this very simple system. So today we're going to finalize the simple design and introduce a new project vehicle that we plan on using to verify that this idea will work on a more modern electric golf cart. So just a quick recap of what the petroleum battery is capable of doing. So in previous episodes, we showed how the dual-purposed alternator works as a DC motor controller, and we have excellent control of the power that we're sending to the DC motor. The throttle on this system is connected to the alternator and not to the gasoline engine. So as a DC motor controller, the alternator is a simple solution. We also demonstrated that the petroleum battery has enough power to pull a 3,000-pound Chevy truck. Now, since there's no hills in Kansas, pulling the truck showed that the petroleum battery is capable of moving the golf cart up an incline. In another video, we demonstrated that the petroleum battery was able to get our vintage Cushman golf cart up to 21 miles per hour. Now, this is interesting. The DC motor was spinning faster than the gasoline engine, so we actually got an overdrive effect. When compared to the original specifications of the Cushman golf cart, the math is saying that we got a 75% increase in speed. I like going fast, and this was a big win. In the most recent episode, we took the petroleum battery-powered golf cart on a 10-mile journey into the Kansas countryside to evaluate the durability of the system. On that road test, the golf cart was driven at 72% of maximum power, and we averaged a little over 19 miles per hour and got exactly 40 miles to the gallon. Of course, once I did the math correctly. Now, as far as durability, the alternator and the DC motor survived, and neither device overheated. So, as you can see, the petroleum battery is a novel idea to restore the functionality of an electric golf cart without investing in expensive and heavy batteries. And the best part is, electric golf carts with dead batteries can be had for not a lot of money. So keep in mind, we're building and testing the system on YouTube for our weekly content. It takes time to develop ideas, test them, and put together videos for the audience to enjoy and learn from. If you're interested in a project like this, consider subscribing if you haven't done so already. And most importantly, don't skip any videos. The reason it's important not to skip any videos is there's a lot of information and topics that have already been covered. My background is in electronics, and to me this is an easy project. The difficult part about this project, at least for me, is trying to keep it simple and inexpensive. Alright, well, let's take a second look at the 140 amp Jeep Liberty alternator that we're using and make one last simple but important modification. This Jeep Liberty alternator was free, and that's the only reason we decided on using it. I reckon any high output alternator would be suitable as long as you're able to disable the voltage regulator and if you can directly supply power to the brushes. Right now we have the alternator partially disassembled, and I've removed the brush holder and this black plastic gizmo, which apparently is not a voltage regulator. It turns out that this is a PWM alternator and it doesn't have a voltage regulator. The voltage regulation is actually done by the ECU in the Jeep Liberty. Anyway, on this alternator we need this black plastic thingy because this is what holds the brushes in place. Without this chunk of plastic, there would be no way to attach the brushes to the alternator case. But there is a problem, and fortunately we have a simple solution. Here, let's look at the diagram. In this diagram, we show the rotor, the PWM power supply that we're using to throttle the alternator, and the little 12-volt battery to power the electronics. So right here are the brushes. This would be the positive brush and this would be the negative brush. The problem we discovered was the negative brush on this alternator is also connected to the case of the alternator, and we can't have that. The two brushes have to be completely isolated from the rest of the electrical system in order for this PWM power supply to work correctly. You see, the PWM output on this guy is on the negative side, so we're essentially PWM grounding the alternator. Right now this works because we don't have the engine and the alternator grounded to the little battery yet. But if we did ground the petroleum battery system to the little 12-volt battery, then that would bypass the PWM ground and we would have a solid ground. The outcome to something like that is we would no longer have a PWM signal going to the alternator, and we would basically fulfill the alternator. The only way to fix this problem is to sever the link between the brush and the case of the alternator. Anyway, on this black plastic thingy, the brush holder attaches to these two threaded holes, and we also connect our wire to these threaded holes. I'll show you how that's done in a minute or so. This tab and this tab are how this thingy attaches to the alternator. This tab is electrically isolated from the brush mounting hole. However, there is continuity from this tab to the brush mounting hole. And that's the problem. We can't have an electrical path from this tab to here. Now, cutting this tab off would be a bad idea because it's also used to attach this thingy to the alternator. So we need to keep the tab in place, but at the same time we need to sever the electrical link from here to here. No worries, this turns out to be easy to do with a Dremel and a cutoff wheel. All we have to do is slice into this plastic thingy a little bit and we can cut the link without damaging anything else. I reckon a hacksaw would also work, but the Dremel is so much easier. Okay, the cut is complete and it wasn't hard to do. Now as you can see in the close-up, we cut through the metal that was embedded inside this plastic thingy and we severed the link from the mounting tab to the negative brush connection. Now we'll have no issue sending the negative PWM signal to the brush. A word of caution, because this thingy is not a voltage regulator, you can't easily get a replacement for it because it's not a part that would typically fail, so be very careful with it. And just for clarity, you can see how these two parts fit together. Well, if I didn't do this, people would complain. As you can see, there's no continuity between the mounting tab and the brush terminal. Perfect. Fast forward a few minutes and the alternator is being assembled for the final time. We have the black thingy mounted to the alternator with the original screws, and we fitted the brush holder assembly. Now all we have to do is attach the wires to the brushes. For the positive wire, I'm using a 1/2-inch tall aluminum spacer with a screw that has a 4mm thread and is 20mm long. The negative wire will also use the same spacer and type of screw. Alright, just to confirm, my meter is showing that there is no continuity between the case of the alternator and this negative brush. Absolutely perfect. Fast forward a few minutes and the alternator's back in the golf cart. Now, the reason it was extremely important to isolate the PWM signal from the regular ground is so I could attach the ground cable from the little 12-volt battery and I could finally use the electric starter. The 212cc Predator engine doesn't come with an electric starter, but an electric start kit is available from the Jungle site for about 60 to 80 bucks, which is a really good deal. So now that we have the alternator sorted out, let's simplify this PWM alternator throttle so we can get rid of the silly MIG welder pedal and go with something a lot nicer. Now on the jungle site, there's another type of PWM power supply that's available, and this one can be paired with an optional foot pedal. You know, a lot of people alerted me to this option, but when I looked it up, I immediately saw that this combo was only rated for 2 amps, and we need at least 8 amps for our alternator throttle. Well, the good news is it's actually a 20 amp system. The idiot that wrote the title put the decimal in the wrong place. Now this is looking like it might be an ideal solution. So the jungle site is offering this as a package deal, and you can get the PWM power supply and a foot pedal for $37. I ended up getting the package deal so I could take the foot pedal apart and see what was in it. It turns out that the foot pedal is a bit on the small side, but it would work. Now, after taking it apart, I discovered it uses a 49E linear Hall effect sensor. And that's great news, because a few weeks ago we bought another pedal, and this one also uses the 49E sensor. This pedal is much larger, and it seems like it would be a lot better for our application. The bad news is the connector on this pedal is not the same as the one on the smaller pedal, so it's going to take some modifications to make it work. Alright, let's take a look at the PWM power supply. So this thing is actually tiny, and it's good for 20 amps, so it has more than enough power for our application. The PWM voltage can be directly controlled by this knob, which is the same as our other power supply. But on this power supply, they give you a place where you can plug in an optional foot pedal or even a motorcycle type throttle if so desired. Anyway, as you can see, there are 2 connection points. The one circled is for the throttle, and this one is for an optional brake pedal. It turns out that this power supply and pedal assembly is made for one of those silly little electric cars made for toddlers. So it's a genuine EV part that'll work in our not-so-EV golf cart. Fantastic! I love it when a plan comes together. Now the power supply also comes with pigtail wires that'll plug into the connectors, which is really cool. And it also comes with a poorly written manual that explains how you can use the power supply in many applications. But since it's a translated manual, not all the words make sense. It's too bad, because this is an awesome gizmo and it comes with hacking instructions, but good luck reading it. So real quick, the foot pedal connects to this connector, and this tiny switch needs to be slid over to the left for the power supply to recognize the foot pedal. Now here's an interesting feature that we'll definitely take advantage of. With the foot pedal connected, we can still use this knob to set the maximum amount of current this gizmo will provide. So if we set the knob to 75% full range, that means when the foot pedal is floored, we'll only get 75% of the rated power. This will come in handy later when we road test the golf cart. So like I mentioned earlier, I don't like this foot pedal, but it's better than all the other options we looked at so far. Another thing I don't like is, when this foot pedal is pressed, this thingy pokes out of the bottom. It seems like this pedal would have to be mounted on some kind of spacer in order for it to work properly. Now this larger pedal is much better, and I took the time to modify the connector so this pedal will work on the new power supply. The smaller pedal will work, but I like this one better. Here, let me show you what I did. So this is one of the extra pigtails that came with the power supply. Basically, I spliced the red wire on the pigtail to the green wire on the larger throttle. Black goes to yellow, and yellow goes to red on the new pedal. Now, I soldered and shrink wrapped all these splices. These wires are really thin, so it may not be as easy as it looks. Alright, let's look at the final design for this ultra simple way to get an electric golf cart back on the road with a cheap gasoline engine and a Jeep alternator. Now remember, the alternator provides the electricity, and it's also the DC motor controller. This is a common sense diagram, and it doesn't show the fuse and a power switch that should be over here. Also over here between the alternator and the DC motor, there's supposed to be a reverse switch. We don't show it because we don't have a switch yet on our buggy. Now this blue wire is the 12 volts that's coming from the PWM power supply. We show an emergency stop switch on this circuit. The e-stop switch is mandatory and not optional. You know, while I was developing the system, I had to use the e-stop switch many times. The e-stop switch is for safety, and it'll prevent the alternator from getting destroyed when things go totally wrong. Over here we show the brake pedal. Now, we don't show it, but the brake pedal is connected to a switch, and that controls a relay. So pressing on the brake will command the relay to open the circuit, and that'll also cut power to the alternator. Now, we're using a 40 amp relay in this circuit because there's no brake switch that I'm aware of that can handle the amp seen on this blue wire. Now, we show the blue wire terminating at the alternator, but in reality, the blue wire goes to the positive brush. Over here, the striped green wire goes to the negative brush, and the stripes are indicating that this is the PWM signal. And up here is the little 12-volt battery. And that completes the basic system. With this system, any electric golf cart should be able to perform similar to our vintage Cushman that we used to develop this idea. Now, if you watched the previous videos, we also added a current limiting device. That's not required on this circuit, so disregard that feature. Now, to tune this circuit, well, the 212cc Predator engine must be throttled up to 3600 RPM. Then you'll floor the accelerator pedal. And likely the engine's going to stall, but that's okay. Back off on this knob and try it again. Eventually you'll find the sweet spot where the engine won't stall and the golf cart will accelerate smoothly. And that's it. You should see the word Simple V1, and that's because this version is the Simple version 1, and it's the bare minimum. Basically, this is all you can do without a microcomputer. We avoided using a microcomputer because we wanted this to be simple. Version 2.0 will have a more complex Arduino microcomputer, but that's not what we're doing today. Now, if you notice, there's no way to keep the battery charged on this simple system. So, the battery will have to be trickle charged on the grid. Now, in version 1.1, we'll retain this simple circuit, but we'll add a simple way to keep the battery charged. Unfortunately, we still need more time to finish testing the charging system, and it's not 100% necessary if you don't mind trickle charging the little battery. I mean, after all, this still is an electric vehicle. Let's go for a ride, and I'll show you how the simple system performs. So on this test ride, I've already calibrated the system by dialing this knob, and we'll get the maximum amount of power without stalling the engine. Let's see how it works. So with the accelerator floored, the golf cart accelerates smoothly and the engine sounds fine, and there's literally no way you can stall the engine with this setting. Now on the amp meter, I'm showing 90 amps when the accelerator is initially floored. On this simple system version 1.0, 90 amps is the magic number. We can definitely get a lot more amps, but it's going to take a microcomputer to manage the voltage and the current, and on this simple system we're avoiding complex solutions. So this is the little gauge where I can monitor the current and the voltage. This gauge isn't necessary, but it's handy to have. Okay, let's floor the accelerator. If you noticed, there was a slight delay when the accelerator was floored until the golf cart started moving. This is a soft start feature that's built into the power supply. Now, the instruction manual provides information on how to reduce this delay, but it requires changing a capacitor on the circuit board. I'm okay with the slight delay, and I have ideas on how to take advantage of it. The current calibration works fine with just a driver, or I can even add a passenger. But without a passenger, I figure this golf cart could probably handle a 200 to 300 pound payload if it were to be used as a utility vehicle. Now, I'm driving with my foot to the floor because, well, that's the way I drive. But this thing can be driven normally if the full throttle lifestyle isn't your thing. Now, when I talk about the throttle, I'm referring to the accelerator that's connected to the alternator. The governor-controlled engine throttle needs to be at the maximum setting, and the engine wants to run at 3600 RPM for the alternator to be most efficient. Reducing the engine speed or the alternator speed will result in reduced performance and may actually cause the alternator to overheat. Remember, running the engine at 3600 RPM will allow the engine to generate peak horsepower for high-demand loads. If the load on the engine's low, well, that's no problem. The governor will automatically adjust the carburetor to provide 3600 RPM at low loads for better fuel efficiency. So if I reduce the engine speed a little bit, the golf cart will still move if you want to putt around, but since the engine is no longer at an RPM where it can make peak horsepower, it's possible to stall the engine if you floor the accelerator. Now, when dealing with electricity and power generation, there's math that can't be ignored. Being ignorant to the math will get you in trouble if you try to go beyond the limits that's dictated by the laws of thermodynamics. On a project like this, it's all in the math. Now, I did the math and the golf cart performs as expected. However, I was extremely surprised to find out this jalopy got 40 miles to the US gallon. Anyway, from the testing we've done so far, the Simple System version 1 is a method that can be used to restore the functionality of an electric golf cart that needs expensive batteries. Now, to prove that claim, we're going to install the Simple System in our newly acquired and much nicer golf cart. Let's head back to the shop and take a closer look at the new project. So the system definitely works on our crappy old Cushman golf cart, But I want to ride in style, so I picked up this buggy for cheap because it has a nasty case of dead batteries. This is the actual project. The Cushman was the prototype. So this is a one-owner 1994 club car, and it's been garage kept its entire life. The batteries failed on this rig about 10 years ago, and it's been tucked away in the back of the garage ever since. Now, it's not perfect, but basically this is an example of what you can find on various websites for cheap. A do-it-yourselfer can replace the batteries for about $900, but if you have the tools, the time, and want to have some fun, the petroleum battery can be fitted for a lot less, and you'll never have to buy batteries again. At least that's the theory, so we're going to find out how easy or hard it is to get this golf cart back on the road with the petroleum battery. Now, just for giggles, let's take the body off this thing so we can have a better look at what's underneath the skin. Since this golf cart was garage kept its entire life, taking it apart was a breeze, and it appears this thing's in great condition. Well, everything except the batteries. Now, the good news is removing the batteries will reduce the weight of this golf cart by 325 pounds. The petroleum battery will put about 50 to 60 pounds back on, but overall will have a significant weight reduction. Now, on this rig, the reverse switch is still intact, and that's great news. I'm going to document how this switch is wired, and I'll include that in the diagram for the simple version 1.0. Now keep in mind, reverse on a series wound DC motor is not as simple as reversing the polarity to the motor. Actually, the polarity to the armatures remains the same, and it's the series field windings that get reversed. Now this golf cart is new enough, and it has a solid-state DC motor controller. The good news is, we don't need this gizmo, because on the petroleum battery, the alternator is being dual-purposed as a DC motor controller. Now, I've already had a look, and bypassing this gizmo is super simple. Actually, we intend to do this conversion without making any changes to the original harness on this buggy. That way, when we're done with this project, we can restore it to the original condition, and my brother's wife can have this thing to cruise around the neighborhood in. Now on the Cushman, it would have been real easy to remove the electric motor and just install a gasoline engine and not have to bother with the petroleum battery. However, on this golf cart, the electric motor is built into the rear axle, and getting rid of the electric motor is not that easy. Now, there are plenty of videos on YouTube on how to gut the electric motor and install a sprocket so a gasoline engine can be fitted. But we ain't doing that. The goal is, of course, to get this electric golf cart rolling again without using batteries or gutting the electric motor. So the frame on this club car golf cart is lightweight aluminum, and as I understand it, the E-Z-GO golf cart uses a steel frame. You know, I may pick up an E-Z-GO golf cart for a future project because steel frames are easier to modify, and that would come in handy for a Kubota Z482 diesel petroleum battery. But these projects need to get views and generate revenue for the channel. So if you like what you're seeing, please share the video so we can continue growing the channel. I really appreciate the support from my patrons and all the subscribers that tune in every week. Yeah, I get it. I may talk too much about the technical stuff, but that stuff is important if someone wants to try a similar project. Version 1.0 is the simple way to get started, and there's plenty of improvements that can be made to the system, but it's always best to start with simple and learn as you go. Well, I had a lot of fun today, and I hope you did as well. I really want to dig into this red golf cart and have some more fun, so I'll see you next time. Until then.